Okay, so thank you, Michael, for that introduction, and good evening to you all. It's very nice to see so many of you here in this very vibrant lecture theatre. So what I want to do this evening is to talk to you about drugs. And it's probably best to start by saying just what I mean by drugs. If we look at the definition that there is of the word, there are two quite distinct meanings. But as far as I'm concerned, we don't really have good drugs and bad drugs. We just have molecules which have different shapes, different sizes, and can have a physiological effect in the body. And of course, lots of the drugs which we consider to be bad drugs are actually still very valuable therapeutic agents. So if we look at this array of pretty pills that's behind us, we can consider them to be drugs or medicines, and I will use both terms interchangeably with no particular implication implied. So that being said, if I look around the auditorium this evening, I can see a number of candidates for long-term or chronic drug use. And I'm not just referring to the somewhat hedonistic lifestyle of our head of School of Life Sciences. I am referring to the range of medical conditions that we manage with lots of different medicines on a day-to-day basis. And this is really the point, that the use of medicines, use of drugs, is such a part of our everyday experiences that we can sort of take for granted their availability and their effectiveness. But what I want to focus on now is really where have these drugs and medicines come from, and more importantly, how can we discover new medicines going forwards? And this is an incredibly difficult task, requiring the interplay of lots of different scientific disciplines, but one which really has an outstanding goal at the end of the journey, which is having an impact on the lives and the diseases that people are suffering with. So let's start with a little journey into the past, and we can try and learn from how drugs were discovered to see how we can use that experience going forwards. So all of the major civilizations have examples of the use of herbs and various natural products as medicines to treat various diseases. And there are some particularly striking examples in these Indian and Chinese texts of the use of natural medicines, which forms part of the very strong traditional medicine culture nowadays. If we come to the beautiful foxgloves here in the middle of the slide, there was an English physician, William Withering, who in the 18th century was noting the use of the folk remedy of these foxglove extracts to treat congestive heart failure, or dropsy, as it was called then. And what was important about this was that William Withering was compiling these extensive case notes. And these case notes were about the efficacy and the safety and how to use the various preparations of the foxglove extract. And this is considered to be really the start of the modern drug discovery, pharmaceutical way of thinking. The references which talk about William Withering are very clear to state that it's the first account in English-speaking literature of the use of foxglove extracts to treat disease, and this is in 1785. But if you scratch just a little bit deeper, you can find that there were in fact records from Welsh physicians in 1250. So 535 years before. Not trying to make a wider point, just that I'd mention it. And from these natural products, we come to these three very smartly dressed individuals. These are the princes of Serendip, and Serendip is the Persian name for Sri Lanka. And these individuals, who coincidentally, I believe, are wearing the costume that my colleague John Atack has promised to wear for his inaugural professorial lecture, which we're very much looking forward to, Michael. And the story that was told about these individuals was dismissed as a silly fairy tale by Horace Walpole, because these individuals were finding their way through life, making lots of discoveries just by chance. And then Walpole coined the term serendipity to describe this behaviour. And then serendipity, or chance discoveries, has actually been one of the mainstays of the early drug discovery that's gone on. And what I'm going to show you is just 4 structures now of drugs that have been discovered in this way. And for those who are not in the area, might be very uncomfortable with seeing chemical structures, I've intentionally shown you three forms of the molecules to make the point that these molecules, the active ingredients of the drugs, are small organic molecules They've got between maybe 20, 30, 40, 50 atoms, and they can be designed and they can be synthesized, which is the point we're going to come to later on. So looking at this molecule, first of all, there was a lab in the 1930s making lots of dye stuffs. They made a series of molecules which were put on the shelf and basically forgotten about. And then during a big clear out 20 or so years later, the molecules were found, tested in some assays and experiments that were running at the time, and found to have a profound effect in anxiety models, opening up the whole field of anxiety medicines and the benzodiazepine class of medicines that these are part of. We have ipronizid, which was a molecule that was being studied in the TB clinics. So patients with tuberculosis were taking this compound. It didn't do a whole lot to treat the TB, but it did cause a feeling of euphoria within the patients. And this then led to the molecule being repositioned as a potential treatment for depression and opened up a whole new class of medicines which could never have been designed, and the mechanism of those didn't get understood for many years to come. And the third one, LSD. So we've got the crop fungus ergot, which people had used as a folk medicine to induce labour. And after the isolation of the active ingredient behind this, Hoffman in the 1930s made a whole series of new molecules, new analogues, to investigate the properties. And he found that the 25th analogue he made, LSD, caused these uterine contractions in the animals he was looking at, but also caused the animals to behave quite strangely. So being a very good scientist of his time, he remade a very large pot of this molecule, took a big spoonful himself, and experienced a range of profound hallucinations, which of course leads on to LSD, a drug in all senses of the word, but also really opened up the start of thinking how we could treat some psychiatric disorders with new medicines. And then finally, we come to the most famous of all the recent serendipitous discoveries. So this is sildenafil. This is a molecule that was being brought forward as a potential treatment for angina, but during the trials initially in healthy male volunteers, there were some very pronounced side effects, which led to the molecule coming forward as what is presumably the most famous pill in the world and the most pop culture reference medicine ever. And I should say thank you to Ben O'Hab in the audience as well for all the things twirly that I have in the presentation going through. So to reuse this great cartoon then, is the logical conclusion of all of this that we should just rely on chance? Well, I guess it might be both a short lecture and, perhaps more disturbingly, a rather short career if the answer is going to be yes. Now, serendipity or chance discoveries are a huge part of all scientific research. They play a big role in drug discovery, but they play an enormous role across the board when we are doing research into new areas. But there have been specific advances in various scientific disciplines which have really transformed our ability to go after diseases in a much more specific way. And I want to just mention three specific advances here. So firstly, we have pharmacology. So pharmacology is the study of the action of specific molecules at specific proteins called receptors in the body that drives a physiological response. And the advances in pharmacology really opened up the whole concept of targeting specific proteins in the body to try and treat a disease. And this led on to some of the huge advances in medicines about half a century ago, and included the work of people like James Black, controlling gastric acid secretion through the receptors that were controlling this within the stomach. Coming on then secondly to cell biology, the ability to make proteins, to study, to manipulate, to purify, to work with isolated proteins provided a huge advance, and that was then followed on more by the revolution in molecular biology and genetics, which has transformed our ability to do targeted drug discovery. And if you don't believe me, then I found this joint quote, which I put at the bottom of the slide, and it's from two individuals who I think we can have complete faith in their truth-telling integrity in all occasions. And I think I can hear murmurs of consent across the room, so thank you. So we come from there to really the modern era of drug discovery. So all of the scientific advances on the previous slide have basically brought us forward to this point where we have on this slide then the 5 top-selling drugs within the US. So these drugs are selling huge volumes of medicines and are making enormous amounts of cash for their parent companies for a very defined period of time, and all of which came about following the scientific advances which have been built on all of the chance discoveries made so far. So I think it's useful just to give you a little bit of a context of what drug discovery and development is. And these are some of the slides that I use at the start of the lectures I do with the final year undergraduate students, introducing them to the concepts of drug discovery before we then go and train them on how to actually do the drug design in the first place. So the first thing to say is that drug discovery and development is an incredibly time-consuming and costly process. It can take about 15 years from start to finish, and before that are many additional years of biological and clinical understanding to really formulate a hypothesis of how to treat this disease. And these hypotheses are so important to get right, and they are very, very challenging to formulate in the first place. And the hypotheses we're talking about is generally that there's a protein in the body that we want to modulate in some way to change the state of the disease in the person. And to modulate that protein, we are going to want to bind a molecule to it, and that molecule is going to be the drug. So this molecule starts life as what we would call a lead, and then we optimize that drug and we confer it with all of the properties we need to make a safe and effective new medicine. When we do this, we are transitioning from what we would call the research phase of drug discovery into the development phase of drug discovery. And this development phase is where we are testing the molecule in people. We're testing the molecule in healthy volunteers and patients. And the costs of doing that are so vast, as you can see on this slide, that it is absolutely essential that we get the chemistry right and we choose the best molecule to go forwards into clinical development. And because we've had all these scientific advances, the question we should really ask ourselves is, why is it still so hard to discover new drugs? And I would argue that the specific design and discovery and development of potential new medicines represents one of the most challenging scientific endeavors we can engage in. And the reason for that is we need to think about what a drug molecule actually is. So what we are wanting from a drug molecule is to have a molecule which can bind to a specific protein in the body, and it can have the effect that we need to help with the disease within the body. It has to have a molecular structure which is safe. It has to be able to be given to people to reach a sufficiently high concentration to drive its effect, and it needs to be overall given at a low enough dose so we don't have other side effects. And this is a really difficult balancing act. So when we design a molecule that binds specifically to one protein, there are often lots of other proteins in the body that have very, very similar structures, and we need to potentially not bind to those because they might have very different functions and be one cause of adverse events and adverse reactions within the body. But if, for example, we want to take a pill, we want to take a drug just as a pill with a glass of water, we then have to navigate an immense set of hurdles to actually get this to be a drug. We've got to get the drug coming all the way through our digestive tract, surviving the harsh environment of the stomach, getting into the intestines, being absorbed into the bloodstream, avoiding all of the metabolic systems. We have the breakdown the molecules. It then has a distributor around the body to wherever we need it, which might be the heart, it might be the lung, it might be the eye, the big toe, wherever it is. And the molecule has to be not toxic, not able to generate anything toxic. It has to be safely given with lots of other drugs, and so on and so on and so on and so on. And the list isn't endless, but it really can seem like it. And one of the big, big challenges here is as you improve one of the properties, it leads to a detriment to one of the others. And as such, the automation of this process is incredibly difficult, and there's a huge amount of subjectivity and experience that comes to bear when we're trying to design new drugs. So that being said, the scientific discipline that takes on the monumental challenge of trying to design new drugs is medicinal chemistry. And medicinal chemistry basically grows out of organic chemistry, and it's the design and synthesis of molecules as potential new medicines. So firstly, that design. This is a really, really difficult thing to do, as I've maybe stressed repeatedly already. It is incredibly challenging to find a molecule which can bind to the protein and be a safe drug. Finding a molecule that can bind to a protein is often a very trivial exercise. Finding a molecule that can do so and can be made into a drug is an incredibly difficult exercise. And when we do this, we have to inform our medicinal chemistry strategy with all of these surrounding disciplines that are on this slide. But then the synthesis, it doesn't really matter how clever we're being in terms of our hypothesis. If we can't actually go into the lab and make the compound, we're never actually going to be able to test these hypotheses out. And this is the really powerful and the really exciting aspect of organic chemistry, which is the ability with precision to make molecules that have never ever been made before. So medicinal chemistry is the process of taking a molecule, a starting molecule, a lead molecule, and optimizing it to make a new drug. We can find that starting point, that lead molecule, by a range of techniques that are shown here. And then once we've done so, we come to what's the mainstay of medicinal chemistry, which is what we call lead optimization. So these are these iterative design cycles to reach our final goal. And from the medicinal chemist side, this is where the really clever bits come in. So we have our starting lead structure, our chemical start point. We come up with hypotheses for how to improve that molecule. We make those molecules, we synthesize those molecules, then we evaluate them, we screen them, we test them in lots of different ways, and maybe in biological assays, physical assays, toxicology assays. We learn from that data, we construct new hypotheses of how to go forwards, and then we go around the cycle as many times till either the wheels fall off and the program is killed and we can't make the drug candidate, or we do get a molecule which goes forward and can start clinical development. And as I said, when we're starting that clinical development phase, the really expensive part of the process, testing in people, the structure of the molecule is fixed. But unfortunately, when we go through this phase, a number of molecules are failing in development. And this graphic taken here shows the reasons why molecules fail in clinical development, and it shows the reasons for 1991 and 2000. And I'm not going to go through this in any detail at all. The only point I want to mention is that the reasons molecules fail can generally, for a number of these, be attributed back to the molecular structure. So theoretically, are within the power of the medicinal chemist to design and control. Now, when we're trying to do something as complex as modify somebody's physiology, change a disease within an individual, there are always going to be surprises, generally nasty surprises. And whilst we can't predict the unpredictable, there are nonetheless general trends which are emerging of the physical properties molecules have that makes them less risky, less likely to fail in development. And as the designing chemist, we have to listen to this information. We have the responsibility then to design the safest compounds we can to take forwards into clinical trials. Okay, so that's given you hopefully a context of what medicinal chemistry is for those of you who weren't so familiar with it before, and what drug discovery and drug development activities look like. What I'd like to do now is just use that context to tell you about one project that I've been doing out of the range that we've been working on over the last few years. And I'd like to dive straight into a disease to do this, which is schizophrenia. Now, schizophrenia, like all psychiatric illnesses, is very difficult to represent and have others conceive of really what it is. But there are a number of online galleries where patients are drawing their experiences of living with these disorders. And I'd encourage you to have a look at some of these, because it really gives you a very interesting and thought-provoking way of seeing the world through really very, very different eyes. So we're going to come on to look at how we're doing rational, modern approaches to treat the disease. But I think it's worth just reflecting on what's happened over the last 150 years on how schizophrenia has been managed and how schizophrenic patients in particular have been managed over that time. It starts about 150 years ago with simply restraint. It comes through to what has to be one of the most weird of all of the things I've seen in this area, which is spinning. So this is where patients would be strapped to a device and spun repeatedly at high speeds in an attempt to rebalance something that was out of order within them. The patients clearly ended up considerably more disoriented and an awful lot more nauseous than when they started. But nonetheless, in Victorian times, this was a very popular and very well-documented and reported technique. If we come into the 20th century, we have the enthusiasm for lobotomies. And within the UK in particular, in the 1940s, we had about 17,000 lobotomies performed. This was soon fell out of practice within the UK, but was carried on in other countries in the US in particular a fair bit longer. And then coming more recently, we have electric shock, electroconvulsive therapy, which is still used for other psychiatric conditions to the present day. So this collectively seems rather crude and a barbaric approach to treat the disease, but I think it's worth reflecting that mental health and mental health issues have a relatively recent acceptance into mainstream medicine. And I would say that our understanding and our resourcing of drug discovery approaches in this area is still inadequate. But to make this point more strongly, and I'll have to confess, slightly more gratuitously entertainingly, this is the Trans-Allegheny Lunatic Asylum, which is in West Virginia. And this lunatic asylum published a set of reasons why patients could be admitted into the lunatic asylum in the late 19th century. There are 86 reasons on this slide. I think if you have time to scan down the list, or maybe from the back, if you have good enough eyesight, you might find, I think, a reason why all of us could have been locked away there. I think I can catch the eye of a few people in the auditorium who are maybe ticking off, or not, hopefully not ticking off at the moment, but hopefully have in the past ticked off a few more of these reasons. It seems you're caught up with a life of vice or virtue. Being in the Salvation Army even would get you locked up. You can tell me at the end maybe what your favourite reason is. Clearly the list is partly here for our entertainment, but it makes the point that there is a total lack of any vaguely serious diagnosis of psychiatric illness going on at this time. So time has moved on. Hopefully our understanding has improved, although I don't think it's improved sufficiently. But returning to schizophrenia specifically, schizophrenia is a devastating illness. It affects a large number of people, and the symptoms come on in late teen, early adulthood, so a devastating time of life for these symptoms to appear. Rather than the conception of schizophrenia as an illness of split personality, it's better considered as a set of distinct symptom domains. So we have the positive symptoms, so these are the quite familiar aspects of the disease, the delusions, the hallucinations, the very disordered thinking, the very florid components. The negative symptoms, the real withdrawal into oneself, and then the cognitive deficits, so the lack of ability to process new information, attend to information, to learn, the difficulties with working memory. And these symptoms in different ratios, different emphasis, create a set of conditions which collectively are termed schizophrenia, and which cause a really devastating impact on the lives of patients and, of course, of their families as well. But importantly, in recent years, the cognitive deficits have been recognized as one of the core underpinning components of the disease. And the hypothesis that if we can improve the cognitive function, so the learning and memory function of schizophrenic patients, then we should be able to improve the overall disease state. But despite that, the current approaches to treat the disease use medicines which have no impact whatsoever on the cognitive domains, and we really have a duty here to bring better medicines to these patients. So our approach to treat the cognitive deficits in schizophrenia was to enhance glutamate neurotransmission. So let me firstly explain what that means, and then secondly tell you why we thought it was a good thing to do. So nerve cells in the brain, or neurons, they communicate with each other either electrically or chemically. And when they communicate with each other chemically, the molecules are called neurotransmitters. And the main excitatory neurotransmitter in the brain is glutamate. So we can simply imagine the glutamate being released from one of the nerve cells, crossing the space between the nerve cells and binding to a specific protein on the surface of the second neuron, which is in this case called the AMPA receptor, and passing the message on. So one nerve cell is talking to the second nerve cell using this chemical messenger as the intermediary. For a brief bit of extra background, the protein it's binding to is a special sort of protein called an ion channel. And this is a protein that sits in the membrane of the cell and can open a pore in response to the glutamate binding through which ions, sodium and calcium ions, flow. And it's the influx of these ions into the cell that drives this onward message. So why do we think that was important? Well, firstly, there are huge amounts of anecdotal, empirical, observational evidence that say that if we enhance glutamate neurotransmission, we improve learning and memory. And if we impair glutamate neurotransmission, we impair learning and memory. So a very, very, very clear association that's built up over many years and many lines of study. And secondly, and this is perhaps a cautionary tale for the wilder members of the audience, although looking around, we're not quite sure who I'm speaking to with that definition, but nonetheless, frequent drug users of drugs such as PCP and ketamine can develop a syndrome which is schizophrenia-like and which causes the drug users to have all of those components of the various symptom domains of the disease. And PCP and ketamine are potent blockers of glutamate neurotransmission, which is clearly the opposite of what we're trying to do here. If you thought that was complex, then I'm going to have to want you to brace yourselves for the next level of complexity. Because you can imagine that our brains have an incredibly precise and controlled and specific set of firing going on within them that really controls everything about who we are and everything that we do. And it is imperative that if we do anything to interfere, to change this signaling in any way, that we do not interfere with the integrity of that signaling. So we might want to enhance it or reduce it, but keeping and preserving the integrity of the natural firing patterns of the brain is absolutely key to developing a safe and effective medicine. And what that means chemically is, to recap then from the previous slide, with the graphic that's on your left, we have a protein that sits, the ion channel protein that sits in the membrane and opens this pore in response to glutamate binding and allows ions to flow through, and that's how we pass the message on through the nerve cell. What we're wanting to do then is to bind a drug molecule to this ion channel protein and stabilize that protein in open conformation to allow more ions to flow through. And that's going to give us a bigger signal and allow us to enhance the neurotransmission, which is what we're trying to do. But what is absolutely essential is that the drug molecule does nothing when it binds to the ion channel on its own. So in the absence of the signaling molecule glutamate, we want the response to be totally silent. And that's the way we're going to preserve the natural integrity of how these nerve cells are communicating, and we're going to preserve the precision and the natural physiological patterns that are going on in the brain. So we want to improve the quality of life of schizophrenic patients. Our approach to do that is to improve the cognitive, the working memory and learning function of those patients. Our approach to do that is to enhance glutamate neurotransmission, and our approach to do that is to stabilize this ion channel molecule, this ion channel protein in an open conformation to allow more signaling to occur. So I'm conscious that is an incredibly complex hierarchy of wishes, but that's basically what goes on at the start of a drug discovery process. This is how we develop the hypotheses of how to go after and treat a disease in the first place. So we set up a number of biological assays, biological screens, to look for molecules which could do just that, could stabilize this protein and give us this potential of a therapeutic agent in this disease. And we found a molecule that could do that. And then we're at this lead molecule stage. We're at this part where we're trying to then optimize the molecule to make it into a potential drug. And there are lots and lots and lots of good things about the molecule, lots and lots of bad things. And we're not going to go through clearly lists of them all. I just want to mention one good thing and one bad thing to give you a sense of how we go about improving a molecule and taking it forwards. So on the good side, the molecule is able to get into the brain. Clearly, we're looking to treat a disease which is in the brain, so Obviously, it makes sense that we can get the molecule into the brain, and that's a good thing we need to achieve. But it's also a very difficult thing to achieve because the brain has around it a protective membrane, the blood-brain barrier, through which it is very hard to get molecules to cross. And even if you do get molecules across, then there are lots of proteins that sit in that membrane, recognize things that are foreign, and throw them back out. The UKIP proteins, we could call them, I think. The flip side, the downside of the molecular profile was that it was very rapidly metabolized. So that means it's being chewed up, it's being broken down by the systems in the body, and it's not staying around long enough to have any effect. So this is where we come into the lead optimization. So how do we keep the good properties of the molecule? How do we improve the bad? And can we merge all this together to make a potential new medicine? So to do this, we draw on all of the tools that we possibly can. And this is one of those tools. So we crystallized our molecule into the protein that we were binding it to. And the protein is shown here in two domains. The blue and green are ribbon representations of this protein. You can see glutamate, that signaling molecule, bound into each of the blue and the green domains. It's the white, red, and blue blobs. And right in the center of the slide, then, you can see our molecule, which is stabilizing this structure and is doing what we want biologically. And the reason this is important is that it allows us to really understand how our molecules specifically interact with the protein. So what we're trying to do is to create a map, a navigational chart, if you like, of the chemical space that we can operate in, because we need to change this molecule. We need to make new molecules based on this compound, but we want to preserve that binding to the protein in the first place. So we use these charts to basically navigate our way forwards when we're going about this project. And so, as the one example then, to fix the metabolism, we said the molecule was being broken down too quickly, so we were able to incubate the molecule with all of the metabolic systems in the body that do this breaking down the molecules. And we were able to use then mass spectrometry as a technique to find out on the red zone that's shown here in the molecule where the molecule was being broken down and where the weak spots were. What we were able to do from that understanding is build hypotheses of, well, what can we do to fix that? How can we improve the molecule? How can we stop that process happening? And what we do is merge that understanding in with the understanding of how the molecules are binding to the protein, because there's no point fixing the metabolism if then we lose the ability to bind to our protein. And this is the juggling act we're always trying to do. But by using and merging these two hypotheses together, we can come up with new and improved analogues, which then are able to overcome this metabolic problem, but also still be actively binding to the protein. And then we go through this process again and again and again and again until we've fixed all the issues that we have and we've got the best overall balance of profile. And then we come up with a molecule like this, which is able to make that breakthrough transition out of the research phase into the clinical development phase and start that very expensive testing in the patients. So that's a snapshot of a program. So you can see the sort of work that I do in the context that I'm doing it in with regard to the medicinal chemistry activities. What I'm going to do for just the last few slides is to close with some more personal reflections and picking up some of the points that Michael mentioned at the beginning, thinking about where drug discovery and development is going at the moment and what we can do in terms of all of the concerns about the big pharma model of drug discovery and how we can still work to bring new medicines to the patient. And the scientific and business literature at the moment is absolutely reveling in the doom and gloom scenarios that there are around pharmaceutical drug discovery and development. There are lots and lots of graphs and statistics being used, but this graph, I think, makes the point quite clearly. So this graph shows over time the amount of return you get for your money invested. It's adjusted for inflation. So if you look at the dotted line that's running from left to right across the slide, that's basically saying if we put $1 billion into research and development, how many drugs would we expect to find over time? And you really don't have to be the sharpest analyst tool in the box to realize that there is a problem with the business model in this case. And there are lots of headlines and facts associated with this, which I'm going to show you, but it's a little bit dry, so I'm going to show you over a musical interlude. And there might be a prize afterwards, the first person who can shout out the name of the band behind the music, if it works. Ah, fantastic. I wasn't sure which part of the age spectrum I was going to be speaking to with this music, so that's the verve, for anybody who wasn't aware. Well done, Tom. And what the verve was telling us is basically that the drugs don't work. And this is really part of the problem. So if we look back again at this whole schematic of drug discovery and development, what we see is that there is a weak point. And this weak point comes quite late on in the process, where quite simply, a lot of the drugs don't work. And the problem here is that this is maybe 10 years or so into this research and development cycle. We've already invested a lot of time, and we've invested, quite frankly, a shed load of money to get to this point. And of course, as I said at the beginning, the basic approach to treat the disease, the hypothesis we're using to go after the disease, is set right at the start of this process. So if we've taken the wrong approach to treat the disease, it doesn't really matter how clever we're going to be on the drug discovery and development going through. We're never actually going to make any impact. And closer to home, the direct consequence of these business models has been the closure of many of the major pharmaceutical research sites within the UK. And this is something that I and many within my group have been directly affected by. And whilst the AstraZeneca-Pfizer debacle has been front page news for some weeks now, the closure of the sites of Rhone-Poulenc, Rora, Merck, Roche, GlaxoSmithKline, AstraZeneca, Pfizer, Novartis, AstraZeneca, the loss of all of these sites has somewhat slipped under the radar of the media. And I think the lack of this story being picked up, the lack of attention paid to the loss of what is one of the huge wealth and innovation generating industries within this country is shocking and is a real failure on the part of the media to represent this in an appropriate way. There are still lots of opportunities and employment opportunities opening up in this area, with lots of new and smaller companies bringing forward pharmaceutical research. But still, the loss of these big sites has been a big blow to the way we can do drug discovery within the UK. And on a slightly lighter note, when I first came down to this area, when I was reflecting on whether to move down to Sussex and take this position, I'd never been to Brighton before. So I took a walk down the pier, and I was being at the receiving end of a pharmaceutical site closure, and I was slightly alarmed to see the list of corporate clients that are included on this fortune teller's wagon, which is still there halfway down the pier. I think on reflection, the quality of advice you're going to get in that wagon is probably the same as the industries have been getting from the sort of management consultancy end of the spectrum. I guess it's considerably cheaper, but still, it was a slightly alarming observation and slightly unsettling at the time. So from there, I mean, my perspective is that we still need new drugs in a number of key areas, and we have to find ways to bring these new drugs through to the patients. So I've just got 4 personal comments on, I think, the way we can go about doing this moving forwards and into the future. So firstly, to try and tackle that late-stage clinical failure, what I think we need to do is to really integrate the early drug discovery process with the understanding of the diseases we're trying to treat. So really mesh these together and don't separate them, as has often happened in the industry setting. We need to stop the huge waste of resource that goes on early on in this process of lots of companies chasing the same target. And we need to find ways to actually get selective tool molecules, selective agents to biologists, to clinicians, to really enable them to answer sensible questions about how to treat the diseases we want to treat. The pharma companies were a fantastic training resource for generations of drug discovery scientists, and their loss has provided a big gap. And of course, we can recognize, being here in a university, that we can respond to that. And I'm very pleased that we've been able to set up a couple of new courses here, the MChem in Chemistry with Drug Discovery and the MSc with Medicinal Chemistry with Drug Discovery, where we have the privilege of being able to train the next generation of drug discovery scientists and to be able to give them the skills that we were very much looking for when recruiting those scientists in industry. And then, of course, finally, big pharma companies have always bought lots and lots of molecules in from outside. They want to have these big, healthy-looking pipelines that are demanded by the shareholders, and they're doing this increasingly at an early stage. And of course, we can respond to that by just diversifying and doing drug discovery in lots of different settings outside big pharma to begin with. And that, of course, speaks to the reasons which stack up behind my maybe quite surprising decision at the time to come out of the industrial setting and come into the university setting. And together with my partner in crime, John Atack, and John, there are, of course, considerably worse photos to choose from, we are jointly running the Translational Drug Discovery Group, and we are committed to doing drug discovery. So either by running major research programs to get molecules into clinical development, we've got a couple of these going at the moment, or by working at an earlier stage and enabling the drug discovery through the activities we do. We've set up labs and collaborations here which very much build on the core strengths of the university, in particular the structural biology with colleagues such as Lawrence and Tony, and the basic expertise in cancer biology, oncology, in DNA damage repair mechanisms that's within the Genome Damage and Stability Centre. And we are now poised to make a realistic contribution in this area. And that's hopefully what we're in the process of doing. It's still very early days for us. We've only been doing this really in anger for about 2 years, but acknowledging that none of us had ever done this grant writing or any of this academic stuff before, we nonetheless have been able to attract a lot of external interest and investment for our projects, which are on the left of the slide, and our PhD studentships on the right of the slide. And we hope we are now poised to make a very serious contribution to drug discovery in this way. And this has all been built on the back of some bold institutional investment from the university. And our challenge now is to take this model forward and really do drug discovery in this different setting. So from sitting in an office on my own about 3 years ago, we're now going to be a group of about 30 to 40 people by the summer. And I would like to say a huge thank you to all of these guys for providing a very stimulating, a very challenging, but particularly a very fun environment to come and do this work in. It's nice watching the guys squirm as the photos appear. It's been a great privilege to have the undergraduates coming into the labs and doing the final year projects and summer work with us. And of course, the collaborators we're working with here within the audience and across the university on all our funded projects. So thank you to all of them, and thank you to you for listening to me this evening.